density. Let's define density. Density means the mass per unit volume. The mass per unit volume is known as density. Okay, density equal mass over volume. So the SI unit of density will be kilogram per meter cube. Okay, so this is the row, letter row that shows that stands for density, and M stands for mass, and over here V stands for volume. It is not velocity, it's volume. Okay. So as the particles are closer together in a liquid, liquids have higher density than gases, and solid also has the highest density when you compare to the gas and liquids. Okay, don't forget this. Why? Because the particles are closer to each other. That's why. So both temperature and pressure have an effect on the volume of the liquid. The density, atmospheric pressure, due to atmospheric pressure, is 101,000 Pascal or 101 kilopascal. Okay, this case stands for kilopascal. And at the normal temperature, it has like we have 20 Celsius temperature in the room. Okay, so do you remember this? As the altitude increases, air gets less dense, and the air is described as getting thinner. So this is going to also affect the pressure. How? When the altitude increases, the pressure is going to get lesser. Okay, it's going to decreases. Don't forget this. So these are some physical quantities and their densities over here. As you see, mercury has 13,600 kilogram per meter cube, honey 1,400 kilogram per meter cube, water 1,000 kilogram meter cube. As you see over here, just when the state of matter changes from liquid to gas, the old density of the quantity decreases. How? Look at here. The alcohol is normally its alcohol is liquid. It's liquid, right? It is 800 kilogram per meter cube. But on the other hand, when you come to air over here, it is 1.20 kilogram per meter cube. Carbon dioxide 1.98 kilogram per meter cube. Nitrogen gas 1.25 kilogram per meter cube. Okay. Why? Because they are gases, and gas state has less density than liquid state. Okay. All right, let's continue. So what is relative density? We have relative density. The ratio between density of a substance to water is known as relative density. Okay, the density of a substance to water is known as relative density. For example, if something has a relative density of 2, it means it is twice dense as water. Okay, if it has 4, it means it is 4 times denser than water. If it's 0.5, that means it is half dense than water. Okay, so we can use the formula density of a substance over density of water to find the relative density of a substance. Okay, so for example, the relative density of alcohol would be, so we know that alcohol has 800 kilogram meter cube per meter cube density, and water has 1,000 kilogram per meter cube. So when you divide 800 to 1,000, you're gonna get 0.8 relative density. Relative density doesn't have any unit. Okay, why? Because over here, kilogram per meter cube for density of alcohol and density of water is kilogram per meter cube. When you divide them to each other, they're going to cancel out each other. Okay, so relative density doesn't have any what do you say, unit. Okay, let's continue. So pressure in fluids. We are going to talk about pressure in liquid generally over here. It depends on depth of the object, and it depends on the height. We are going to call height or depth the density of the object and the gravity. Okay, the gravity we are going to take 9.81, or sometimes we are going to take as 10 Newton per kilogram. So it depends on these three physical quantities: height or depth. Over on the other hand, this stands for density. Okay, it is rho. It is not P. This is pressure over here. This one is pressure, but this one is rho. It stands for density. This is density. This is pressure. Okay. So we are gonna find our pressure, the SI unit of pressure, as Pascal. Okay. So we have here depth of the fluid in meter, and we are going to have density of the fluid as kilogram per meter cube, and the gravitational force or gravitational field strength 9.81 Newton per kilogram or 10 Newton per kilogram. We are going to take it, okay? Again, don't mix P and rho over here. This is P, okay? This stands for pressure, and this is rho. It stands for density of the object, okay? It's a Greek letter. Don't confuse them. All right. So you shouldn't forget this. Pressure acts equally in all directions to a body, okay? This is very important. So when, for example, when you go to the swimming, you're going to feel pressure on all over your body. This is because of pressure acts equally on all directions, okay? Don't forget this. So there's a small difference between height of the column above you and bottom you, but essentially we are going to say that the pressure is the same, okay? So pressure applies on you is the same. Don't forget this. There's another important part. So what about the effect of the atmospheric pressure? Yeah, the atmospheric pressure, when you go to the swimming, you're going to have two kind of pressure on you. One of them is going to be pressure due to atmospheric pressure. The other one is going to be pressure due to fluids, okay, or liquids that you are swimming on. So we are going to use this formula: pressure equal atmospheric pressure plus liquid pressure to find the total pressure on a body, okay? So remember, the atmospheric pressure at sea level is 100. This is 100, 1000 Pascal or 101 kilo Pascal, okay? The atmospheric pressure. It is 101,000 Pascal. So let's do a question about this. As you see over here, before we go to the question, let's explain this. So when you swim in the water, you have atmospheric pressure above you, as you see, and you're going to have the pressure in all directions. Like you're gonna have pressure in all directions on your body due to liquid pressure, okay, or fluid pressure. So you're gonna have two pressure on you, and when you add them, you're gonna find the total pressure that acts on an object, okay? So let's do a question. Determine the pressure acting on a diver 20 meters below the surface. So here we are going to use this formula: pressure equal atmospheric pressure plus liquid pressure. Remember, the atmospheric pressure is giving you 101,000. So 101,000 Pascal here, atmospheric pressure, 20 plus 20 times 9.81 times 1,000, okay? When you do that, you're going to find around 301,000 Pascal pressure, or when you convert this to kilopascal, you have to divide the 1,000, okay? When you divide the 1,000, you're going to convert the kilopascal. So they're going to simplify or cancel out each other. So you're going to have 301 kilopascal over here, okay? So total, if you dive 20 meters below the surface of the water, you're going to have this much pressure on you, 301,000 Pascal, which is very high. So be careful when you dive, okay? All right, now it comes to the Pascal principle. What is Pascal principle? So when you apply pressure on an enclosed fluid, it is going to transmit it equally to all part of the object, okay? Just a second. So we call this Pascal's principle. For example, let's say you have your you take your, like, say, toothpaste. When you squeeze your toothpaste, you're going to see that you're going to feel that the toothpaste are going to transmit it equally to all part of the enclosed object, okay? So this is because of the Pascal principle. So we call this principle Pascal principle. So where do we use Pascal principle? Generally, Pascal principle is used for hydraulic machines. What is a hydraulic machines? Hydraulic machines use the water's incompressibility to do work, okay? So Pascal principle applicable for hydraulic machines, and hydraulic machines rely on the incompressibility of liquids in order to do work, okay? So this is Pascal principle. The pressure applied to an enclosed fluid transmitted every part of the fluid equally, okay? So here we are going to use a formula over here. F1 over, you're going to have an area over here. F1 over A1 equal to F2 over A2. This is a hydraulic press over here, hydraulic machine. As you see, when you put an input force over here, you are going to have an output force on the other hand. Okay. So F1, generally F1 is smaller than F2. Why? Because when you apply a less force, you are going to have a larger force at the output. And the area 1 also smaller than area 2. Okay, so the pressure over here is greater than pressure over here. Why? Because area here is smaller than area over here. Okay, so we're going to use this formula. F1 over A1 equal to F2 over A2. Okay. Okay, so the pressure over here is throughout the liquid is going to be the same. Why? Because you're applying this the force over here, and it's going to apply the same force to all fluid, so it's going to be the same. Okay. So the piston on the right has a larger area, as you see over here. It has larger area. So the force from these pistons is equal to P over P times A2 or F2 over A2. So again, we're gonna get at the end this formula, F1 over A1 equal to F2 over A2. Okay. So let's pass this part. Okay, hydraulic machines. Let's go to the hydraulic machines. Pascal's principle has many applications. It's one of the simplest one is hydraulic lift. So as a hydraulic lift is a hydraulic machine used to raise heavy objects. You can see this one where in the garage or like when you go to the like mechanics, you are going to see that the hydraulic lifts over there. They used to lift cars and they fix the cars by using that. Okay, hydraulic lift. So hydraulic press, this is an hydraulic machine also used to shape metal or compress materials into smaller volumes. You can see this one when you go to when you visit the factory. You're going to see these hydraulic presses. They shape the metals over there. They made cars, for example, by using the hydraulic presses, or they made shapes of the metals by using hydraulic presses. So hydraulic brakes, this mechanism used fluid to transfer pressure from a foot pedal to push brake pads onto the brake disc. So you can see this in the cars. When you drive the cars, you can see the hydraulic brakes over there. Okay. So what is the difference between atmospheric, gag, and absolute pressure? These are the three types of the pressure. So the first one, absolute pressure. The absolute pressure is actual pressure at a given point. Okay, the actual pressure at a given point. Atmospheric pressure, we already know it is the pressure due to atmosphere. Okay, and gag pressure, the difference between absolute pressure and atmospheric pressure. So when you take the absolute pressure, let's say absolute pressure is 200,000 and atmospheric pressure 101,000. So when you take a difference of these two, you are going to get gag pressure. Okay. Gag pressure is the differences between absolute pressure and atmospheric pressure. So the differences between absolute and atmospheric pressure. So for example, there is an example over here. Let's say the gag pressure of the system is 49 kilopascal. To find the absolute pressure, what are you going to do? You know that the atmospheric pressure is 101,000, right? The gag pressure is 49,000. And we are going to find the absolute pressure, PS. To find the absolute pressure, we are going to send the atmospheric pressure over here on the other side of the equation. So it's going to change its operation. It's going to be positive. So the absolute pressure will be equal to gag pressure plus atmospheric pressure. So the gag pressure is giving us 49,000 Pascal or 49 kilopascal plus the atmospheric pressure. We know that is 101,000 Pascal. When you add them, you're going to find the absolute pressure 150,000 Pascal. Okay, this is going to be absolute pressure. So a gag pressure relative to atmospheric pressure, it's possible to obtain negative readings like negative 10. It could be. That means it's going to be 10 kilopascal below atmospheric pressure. Okay, when you get the negative 10, that means it's going to be 10 kilopascal below the atmospheric pressure. So gag pressure can be negative, but atmospheric pressure is already known as 101,000 positive. Okay, 101,000 Pascal. It is positive. but gag pressure can be negative. And that negativity shows, that negativity will show that the gag pressure is below the atmospheric pressure. So we use it. There are many devices that we use to measure the pressure. Pressure. The first one, it is going to be Burden gag. This is the shape of the Burden gag. So we use this to measure the pressure of gas. You can see this when you watch the movies. Generally, the movies like happens at the basement. You can see this Burden gag over there. Okay, it measures the pressure of gas, the Burden gag. So the second one is manometer. Manometer, as you see over here, this is shape of the manometer. It is a U-shaped tube filled with the liquid, which is used to measure pressure. Okay, over here, this is the liquid. The black part is a liquid. It can be water, it can be any other thing that you wanna measure the pressure. If one side of the manometer is connected to the system under pressure, the liquid will move. Okay, so for example, when you apply the pressure over here, the liquid will move, and you are going to be able to find the pressure over here. So here there is an example, as you see on the right part. Pressure of gas. If water-filled manometer was connected to a gas supply, the height difference is BC. Over here it's going to be 9 centimeter. The pressure would be, so we have atmospheric pressure again, 101,000. We have to convert this 9 centimeter into meter, which is going to be 0.09 meter. Okay. We know that the pressure, the density of water is 1,000 kilogram meter cube over here, and we are going to take the G as 10 Newton per kilogram. When you do this, you are going to find the pressure of the gas 101,900 Pascal. Okay. So what is the gag pressure over here? When you subtract atmospheric pressure to the gas pressure, this is actual pressure that we find. We are going to find around 900 Pascal gag pressure over here for this system. Okay, the difference is between atmospheric pressure and absolute pressure. So we are going to find the pressure of a gas by using the atmospheric pressure plus this 8 cb, the height of the column, the gas pressure over here, okay, times density of liquid times gravity. We are going to use this formula to find the pressure of a gas, okay. So let's continue the forces in fluids. So object seems less heavy in water. Why? What is the reason? This is because of if the water has like higher density than the object, the object will float on the water. Okay, this is because of that. This is because of the density differences between water and the object. Okay, so there is a force from the water that pushes you up, acting against gravity. This force known as buoyant force or upthrust force. Okay, upthrust. When you see upthrust force, upthrust, actually you are going to say that this is called for buoyant force. So it is arises due to the fact that as pressure increases with depth, if you immerse an object in the fluid, the pressure on the bottom will be greater than the pressure on the top. Okay, the pressure on the bottom is going to be greater than pressure on the top. So we are going to use the formula. The differences between height times density times gravity is going to be equal to change in this over here. This delta shows the change in pressure. Okay, so the difference in pressure can be found by using this formula. We're going to use this formula at the bottom. Okay, change in height times density of the object times gravity. Okay, so the difference in pressure means there is a difference in force acting on top and bottom. Okay, here there is going to be different force, here there is going to be different force. Okay, it means that so the force on the bottom is greater, and so there is net force upwards. So since this force is greater than this one, the net force will be upward. Okay, so the size of buoyant force depends on a number of factors, including density of the fluid and the volume of the object. Density of the fluid and the volume of the object are going to help us to determine buoyant force for the object. Okay. So now we have apparent weight. What is apparent weight? So remember that object can immerse in water. Okay. Why? Because their weight is less than the water. That's why. Obviously, their weight has not changed. Okay, their weight is the same, but since you are changing like its place from one place to another one, it can immerse or it can float on the water. So the buoyant force push upwards, acting against the object weight, and so the weight appears to drop. Okay, due to buoyant force, you're going to observe that the weight is like dropping or decreasing. Okay, so the apparent weight may be calculated by using this formula: weight apparent weight equal weight of the object minus buoyant force. Okay, weight of the object minus buoyant force will give us apparent weight. So gases like air also provide a buoyant force, but it is usually too small to need thinking about it. So we ignore that. That's why. So this equation is going to be more commonly used. Okay. So buoyant force will be equal to weight minus apparent weight. Okay. When you send the buoyant force over here and apparent weight over here, you are gonna have this equation. So buoyant force will be equal to weight minus apparent weight. Okay. So Archimedes principle stating that the weight of the fluid displaced by an object is equal to the buoyant force acting on it. So let's say there is a cup of water, and when you put like a rock inside of the water, some water displays to outside. So we are going to call this uh, buoyant force. Okay, this is going to be our buoyant force. If you are looking for buoyant force, this displaced water, this amount is going to be our buoyant force. So why? Because of the Archimedes principle. Okay, so Archimedes realized that when an object is immersed in a liquid, it displaces a certain volume of the liquid. Okay, Archimedes realized this. He determined that the weight of the displaced fluid was equal to the buoyant force. Or his own words, any object wholly or partially immersed in a fluid, a buoyant up by a force equal to the weight of the fluid displaced by the object. Okay. In other words, the buoyant force acting on an object is equal to the weight of displaced fluid. This part is very important. The buoyant force acting on an object is equal to the weight of a displaced fluid. So buoyant force here is going to be equal to weight of a displaced fluid. So the greater the volume of liquid displaced and the greater the buoyant force will be that. Okay? The greater the volume of the liquid displaced, the greater the buoyant force of the object over there. Okay? So we can modify the equation over here by applying the Archimedes principle. Apparent weight, remember, it was equal to weight minus buoyant force. So we know that buoyant force equal to weight of displaced fluid. So then apparent weight will be equal to, when we put here, when you replace buoyant force by weight of displaced fluid, we are going to have this formula. Apparent weight equal weight minus weight of displaced fluid. Okay. So floating and sinking, uh, floating and sinking depends on, again, the density difference between water and the object. Okay, the density difference between water and object. Here there are three objects. One of them is over here is in the middle standing. One of them is at the top floating, and one of them is just standing over there. So the A, let me just check one thing. Okay, so for A, so the weight of the object is greater than the buoyant force. That's why the stone will sink over here. Okay, the weight of the weight of the object is greater than, or the density of the object is greater than density of water. That's why it's going to sink over here. Here, the density of water and the density of the object, like the force, buoyant force, is equal for the B. Okay, the density are equal. That's why it's going to float over here. And here, the density of water is greater than density of object. That's why the object will just stand at the top. Okay, the balloon over here will rise because of the buoyant force difference between water and the balloon. Okay, the buoyant force of the water is greater than the the buoyant force of the balloon, and this is the reason. Okay. So what about density? Again, if density of the object is greater than the density of the fluid, it will sink. Okay, the density of the object is greater than the density of the fluid, the object will sink. The density differences. This means we need to consider the relative density between the object and the liquid. Okay, relative density between object and the liquid. If the relative density is less than 1, the object will float. Okay, this part is important. The relative density of the object is less than 1, the object will float. Okay, if the relative density is greater than 1, what's going to happen? Then the object will sink. Okay, so if the relative density is equal to 1, what's going to happen now? The object will just float on the top, because the density of the water and the density of the fluid and density of the object will be the same. When they are the same, it is going to just stand over there. Okay, so relative density is important. If it's great, like if it's less than 1, it is going to sink, it's going to float. If it's more than 1, it is going to sink. Don't forget this. If it's equal to 1, it is just going to stand in the middle. It is going to be equal to, because density of the fluid and density of the object will be the same. Okay, so there is a question over here. A floating wooden block has a volume of 0.4 meter cube and displays 0.3 meter cube of water. Determine density of the block. So remember, these two volumes, you have to subtract them. Okay, when you subtract them, you're going to get the volume of the object. Okay, when you get the volume of the object, what is this? A wooden block. You have to know that what is the pressure on the wooden block. So the weight of the wooden block, you are going to find it, and at the end, you are going to see this formula over here, the equation over here. When you find, we are going to see this equation and to find the density of the wooden block. Okay, P object times V object equal to P fluid rho object times V object, density of the object times volume of the object equal to density of fluid times volume of the fluid. Okay, so here the wooden block we are talking about, you put inside of the water. So you know that water has, let's put it here, the object, the volume of the object is 0.4 times rho object equal to 0.3 times water has 1000, remember 1000 kilogram meter cube density. When you do this, you are going to find 300 over 0.4. Okay, and here you can multiply here by 10 and by 10, and denominator and numerator is going to be 3000 over 4. That is going to be what? 750 kilogram per meter cube. So the wooden block has the density of 750 kilogram per meter cube. Okay, you know that the volume of the object is 0.4 over here. The volume of the water is given you 0.3 over here. You know the density of water is 1000 kilogram per meter cube. When you apply the formula over here, you are going to see the wooden block has a density of 0.750 kilogram per meter cube. Okay, this is going to be the end of the class. Do you guys have any questions? Let me just a second.